Welcome. In this session, we'll see the step response of an LDI system. Means if the system is LDI, then what's the step response of that system? In other words, we know as an LDI system is characterized by the impulse response of the system. Impulse response is h of n, and we are assuming this is given. So the corresponding output will be y of n, and we know we can write y of n as convolution between x of n and h of n. And this we can write it like this. This can be written as k running from minus infinity to infinity, x of n minus k, h of k. So this is the output of a system, any LTI system. Now our goal is to determine the step response of the system. Means if the input to the system is step. So in other words, if x of n is u of n. If the input to the system is u of n, what will be the output of that system? That's the meaning of step response of the system. So to calculate this, we can write y of n becomes replacing x of n by u of n here. So we'll have k is running from minus infinity to infinity. And instead of x of n minus k, now we have u of n minus k, means replacing x of n by u of n. That will give us u of n minus k, h of k. So this is the step response of this system. Now we'll use the definition of u of n. We know u of n. Let me go back to this u of n. We know u of n is defined as equal to 1 when n is greater or equal to 0, and it's equal to 0 when n is less than 0. This is how we define u of n. Same way we can define u of n minus k now. So u of n minus k is equal to 1 when n minus k is greater or equal to 0. When this n minus k is greater or equal to 0. And so R, I can write this condition same as when n minus k is greater or equal to 0, or n is greater or equal to k. Since my variable in this summation is k, not n, so how will I define k? So when k is less or equal to n, I can write this statement same as when k is less or equal to n. Means this k never becomes greater than this n. In this summation, the k never becomes greater than n. Using this restriction means when n minus k is greater or equal to 0, we arrive at this, means k never becomes greater or equal to greater than n. So substituting this, we are left with k running from minus infinity to n, yn, because k is always less or equal to n, h of k. So this is the response of the system. Means when the input to the system is u of n, the output of this LTI system is this. And let's denote this by a special name, S of n. S of n is the step response of this system. And this is the step response of this system. This is the step response of this system. So this is the step response of the system. When the input to the system is u of n, the output of that system is, let's denote it by a special name, S of n. This is not delta n, this is S of n. S of n is given as simply summation k running from minus infinity to n, h of k. So this is the step response of this system. This is the step response of this system. It is simply summation k running from minus infinity to n, h of k. This is how we derive the step response of this system. Now I want to manipulate this step response. So I can say S of n is k running from minus infinity to n, h of k. Now I can write it also like k running from minus infinity to n minus 1, h of k we are left with the last value, that's nth value. So I can write that here. This is h of n. Now we know h of n is the impulse response of the system. S of n is the step response of this system. Alright, so from this you can show the intuitive idea. What's the step response? Equal to sum of all the values of this impulse response up to time in step n. So from this formula you can see that S of n is simply the sum of all the previous sample values of h of n up to this time in step n. So simply if you have to determine the step response, just add the impulse values up to that instant of time. So if you have to determine the step response up to time n, means any time instant n, add all the sample values of h of n. This is how you can interpret this. Now let me call this equation 1. Let's call this equation 1. Now I can also write in this equation, if I say in this equation A, if I replace n by n minus 1, replacing n by n minus 1, I'll have s of n minus 1 is equal to summation k running from minus infinity to n minus 1 h of k. You can check it if you put if you replace n by n minus 1, then just put n equal to n minus 1 in A, you will get this expression. Now have a look at expression 1 and 2 and subtract these two. So if you subtract these two, what you will get? You will get s of n minus s of n minus 1 is this quantity will cancel with this quantity and we are left with h of n. Okay, so I can rewrite it like this. So h of n is simply s of n minus s of n minus 1. Sorry. So this is 1. So this is if the step response of the system is given, you can calculate the impulse response from that. And if the impulse response of the system is given, you can calculate the step response from that doing this operation. So this is equation B. So from equation B, equation A, you can calculate the step response if the impulse response is given. From equation B, you can calculate the impulse response if the step response is given. All right, so this is the relationship between the responses minus the responses of the system. So first, if the impulse response is given, means h of n is given, then step response can be calculated like this. Again, this is now delta n, this is s of n. S of n is simply the sum of all the previous values of h of right, h of k. This is simply h of k. So this is how we write the step response. Same way, if the step response is given, now if the step response is given, then impulse response can be calculated like this, just subtracting the current and previous value of this step response. So this is how we calculate step response and impulse response of a system based on which is given. All right, so our main topic was actually this. This is how you calculate the step response of the system whose impulse response is given. Now I want to go back to the signals, means delta n and u of n. I want to illustrate the relationship between delta n and u of n. What is the relationship between delta n and then see that this relationship is the relationship between the responses, means the output of the system. Now what's the relationship between these two? And now if you plot delta n, you know delta n is 1, 0, at these places it is 0, and only at these instants of time it is 1. Same way u of n, so u of n, I can draw it like this. 1, this is 1, this is 1, and so on. So this is 1, sorry, 0, 1, 2, and so on. And this is n, this is -1, this is -2. So the negative value u of n is 0. So these are the two sequences, u of n and delta n. Now I can write the delayed version of u of n. If I write the delayed version of u of n, if I write the delayed version of u of n, let me clear this. So this is, let's suppose u of n minus 1. So this is u of n minus 1 minus 1. This is a delayed version of this. So this is 0 at -1, its value is 0, at -2, its value is 0. And it is positive for 1, 2, for 3, and so on. This is a time axis. All right, so this is u of n minus 1. Now see, if you subtract these two, if you subtract from u of n minus 1, what will be left with? So if we subtract these two sequences, means you can check the subtraction between u of n and u of n minus 1. What will be left with? You can see at -1 its value is 0, it is 0 here, so it will not change, so it will be 0 here, it will be 0. Similarly at -2 it is 0 here, it is 0 here, so it will be 0. At -3 it will be 0. Now at u of n at n equal to 0 is 1, but it is 0 here, so the value will be simply 1. So the value is 1, and at 1 the value here is 1, at 1 the value here is 1, so it will be 0 when you subtract. Similarly at 2 the value here is 0, 1, at here the value is 1, so it will be 0 again. So these sample values are 0. So you can now check. If you subtract u of n from u of n minus 1, you are left with a sequence that is same as delta sequence. So you can say the delta sequence u of n is u of n minus 1, u of n minus 1. See, the corresponding response of an LTI system due to delta n is termed as h of n. Similarly, corresponding response we term it as s of n. This we term it as s of n minus 1 if the system is LTI system. You can see they are also related. So if delta n is related to u of n by u of n minus u of n minus 1, the output responses are also related by the same relationship. You can check it. So this is the relationship between delta n and u of n. Now, how do you express u of n in terms of delta n? See, if I have delta n, let us do that relationship. So if we express delta n, sorry, u of n in terms of delta n. First, let's draw delta n. So this is our delta n. Rest of the samples will be 0, 1, 2, 3, 0. So this is our delta n. Same way we can say this is delta n minus 1, one is delayed version of this. So this will be n, and this will simply be 1, and rest of the samples will be 0. So this is 1, 2, 0, minus 1, minus 2. These samples are 0. Same way we can draw delta n minus 2. And this is n. So this is our delta n minus 2. The sample values are non-zero only at n equal to 2. Rest of the samples are 0. So the rest of the samples are 0. So this is 0. This is minus 1. this is -2. Now so on. If you continue this delta n minus 3, delta n minus 4, delta n minus 5, and if you add these sequences, what will you get? You will get the setup sequence. You will get this sequence. You will get this u of n. So u of n is simply equal to delta n plus delta n minus 1 plus delta n minus 2 plus delta n minus 3 plus so on, and this will continue up to infinity. In other words, you can write it as a summation. This is delta kn running from 0, sorry, it's not from infinity, it is k running from 0 to infinity delta n minus k. So this is the relationship between u of n and delta n minus delta n. So this is the relation. So you can get delta u of n from delta function, just taking the summation, and you can get delta n from u of n, just subtracting u of n and u of n minus 1. This is how we obtain u of n and delta n. And same way the relationship between the output responses is also. So this is the relationship between these two sequences. Now in time domain, if you remember, in continuous time domain, sorry, not time domain, in continuous time domain, we say delta t. What is the relationship between delta t and u of t? U of delta t is simply the differentiation of u of t, and u of t is simply minus infinity to t integration of this delta term data. Now have a look at this. Compare this with this discrete term. Delta n is u of n minus u of n minus u of n minus 1, and u of n is summation k running from minus infinity, not infinity, k running from 0 to infinity delta n minus k. So this is the relationship in continuous time and discrete time. Same way, if you see the relationship is in terms of responses, what is the response relationship? Response means when the input is delta n and u of n. So if any one of these two is given, you can calculate the other. In continuous time domain, the impulse response you can get from step response, just differentiating this marker. So you can calculate h of t by differentiating the step response, or you can calculate the step response by integrating the impulse response, t, and if by that s of t. So this is the relationship in continuous time domain. So this is the relationship in continuous time domain, and here h of n, by the way, h of n you can get, meaning the discrete versions of this will be simply s of n minus s of n minus 1. Please remember, this is not delta, this is s. And same way, s of n you can get as k running from minus infinity to n h of k. So this is the relationship between the responses. As if impulse response is given, you can get the step response in continuous time domain like this. and in discrete time like this. If step response is given, we can get the impulse response by doing. So this is how we calculate step and impulse response. Now let's calculate the step response of a system whose impulse response is h of n is alpha raised per n u of n. So calculate the step response if the impulse response is this. So step response will simply be s of n summation k running from minus infinity to the n h of k. So substituting the value, substituting h of k here. In short, replacing n by k, we have alpha raised per k u of k. So using the definition of u of k is 0. Using the definition of u of k, this is equal to 1 when n is greater or equal to 0, and this is equal to 0 when n is less than 0. Using this in this summation, we'll get k from running from 0 to n alpha raised power k. Right, so this is simply as I'm using and substituting this definition in this here. So this will be alpha raised by 0, alpha raised by 1, alpha raised by 2, so on plus alpha raised by n. So this will be the last term. Now you can see alpha raised by 0 is 1 plus alpha plus alpha square plus so on, alpha raised by n. And you can see this is a GP with common ratio r equal to alpha. So the sum of this GP is 1 minus alpha raised by n. The last term is n, so it will be n plus 1 minus alpha. So this is the impulse response, sorry, step response of this system. So this is the step response of this system whose impulse response is alpha and u of n. So this is how we determine the step response. In the next session, we'll determine if the input is a sinusoidal. If the input is a sinusoidal function, what will be the output? All right, let me stop here.